Department of Computer Science, National Taiwan University. Actually, he's a research institute in machine learning, data mining, and numerical optimization. He's a world-leading expert, not only in machine learning, right, but also in software design in machine learning. So to me, actually, he's the godfather of software design in machine learning. And his LibSVM package is the most widely used package and most kind of frequently cited package in machine learning. I benefited a lot from LibSVM when I was doing my PhD. And he's also a IQE fellow, SM fellow, and AAI fellow. So, okay, oh, by the way, let's welcome him.
Well, thank you all. So it's my pleasure to be here. So today I'm going to give you a talk about our recent work on text classification. So the title of my talk is Algorithms and Software for Text Classification. So I'm from National Taiwan University. And here's the outline of the talk. So first, we will give a brief introduction about text classification and also the software package that we are currently working on called the LibMultiLabel. Then the second part, during that process, we identify that right now in the whole community, the inappropriate use of machine learning methods is actually a big concern. So I'm going to show some very interesting examples. That's actually the major contents of the talk. I'm not going to talk about the third part for two reasons. First, I don't have enough time. Second, tomorrow in the workshop, I need to give another talk. We need to have some materials there. So, so that part will not be included in the talk today.
Most of them will not go to the workshop.
So then there's a conclusion. Now for the first part. So what is text classification, or say document classification? Here I show a very simple example. So I have two data instances here. They are actually from a very famous data set called RCV1. That's a Reuters news documents. Now for each data, for each line, that means one document. I have the tab to separate the two parts. The first part means labels of the document. And for the second part, that includes a set of words, let's say a sequence of words. That's about the document. So typically, such a line corresponds to one data instance for document classification. And there are several types of document classification problems. Traditionally, we do binary or multi-class classification. So that means each document is associated with one single label. So if you do binary, that means 0 or 1. So only one label. And the multi-class, if you do say digit recognition, that's exactly 1 from 0 to 9. Or multi-label is a different situation. That means each document can be associated with multiple or maybe 0 labels. And this is actually more difficult. This area has actually been well studied. However, we find out that actually tools to easily and conveniently solve users' problems are somewhat lacking. So our motivation was at one time point, I worked with a company on medical document classification. So I need some tools. And I couldn't find out very good tools for doing that. So in the end, we tried to develop one by ourselves. So why right now it is difficult to have a good tool for users to do document classification? one issue is that there are so many considerations. So for example, if you are doing multi-label classification, you can see paper listing like more than 10 possible evaluation criteria for multi-label classification. So for example, you are probably aware of things like micro or macro F1. Those are the so-called accuracy-based criteria. But in many other applications, people consider things like precision or NDCG at K. That's the so-called ranking-based criteria. And for many users, they have no clue like what are appropriate criteria for them to use. And also, situations for different types of data can be very different. If now you have a data set with, say, less than 1,000 labels, and now you have a different data set with, say, 1 billion labels, then the way to handle them can be quite different. So that's another challenge. So our goal is to have some way to guide users to solve their problems. But this is indeed very difficult. So far, say, for example, for multi-label classification, somehow we couldn't find some definitive recipes to handle all possible situations. So it's like now if one user comes and say, okay, my data is like this, then can we immediately tell what are possible good approaches for handling their data? It's not easy. And the things are a bit beyond what current automated machine learning can do. Usually, AutoML is good on things such as hyperparameter tuning, those things which are more well-defined. But now we are in a less well-defined situation. And right now we are developing a package called the LibMultiLabel. This is an ongoing development for text classification. And here's the web address of that software package. Well, it is a simple tool. And right now with the following functionalities. First, we try to provide end-to-end services from raw text to final evaluation and analysis. But this is important because now we want to be able to handle raw text. So I think some time ago, for many document classification works, they somehow separate things to 2 stages. One is to convert raw text to numerical features, then go to call some machine learning solvers to do the learning job. But now, for a good tool, you need to do an end-to-end service. Then, of course, we support common neural network architectures. And then some basic things like linear classifiers, they are included. And hyperparameter selection is important. Therefore, we try to include the functionality of easy hyperparameter selection. We hope to be able to solve different types of data. Therefore, we support binary multi-class classification as well as multi-label classification. But as I said, we haven't had a good recipe yet for guiding users to effectively solve all their problems. Then, of course, we want to achieve this. But in our efforts for achieving this, through that process, we find out that the inappropriate use of machine learning methods by many engineers is actually now a big concern. So I'm going to share some very interesting stories. So now for this part, I'm going to argue that now for users of machine learning methods, sometimes they just don't use those methods appropriately. And this is actually not very good. For we machine learning researchers, we should try to help them to improve their results. So I have two stories here. The first is about the inattention of parameter selection. So I'm going to tell a story here. So about parameter selection in machine learning. Actually, everyone here knows that for machine learning methods, hyperparameter selection is extremely important. But the problem is that in practice, people may not pay enough attention. And this is a short ACL paper. In that paper, we show a very intriguing example. And in that example, you can see that even some minor inattention can cause elusive research progress. So just some minor inattention, then there are some problems. Now let me tell you more details about this story. This is about multi-label classification for medical code prediction. There's a famous data set. This is right now a standard benchmark data set for medical code prediction. It's called MIMIC3. It is a multi-label data set with almost 9,000 labels. So this is a very standard benchmark. As I said here, it is the most widely used open medical data set. So then, of course, there are many works studying this data set. Then there's another set. Let me call it MIMIC350 here. This is a subset of the full set. Because some people say, well, at some time point, some people are interested in the 50 most frequently occurring labels. Therefore, they collect a subset of data having those 50 labels. So now this new data, this subset, let's call it MIMIC350. Then also many people go to study or to use this data set for evaluation. So now we have two data sets. Then in 2018, there's an influential work in medical code prediction. In this work, they proposed a network architecture. They call this network architecture CAMO. Anyway, it's a convolutional neural network with label-based attention. So, well, you don't need to know details here. Suppose this is an effective network architecture. So here I say that it is an influential deep learning work achieving state-of-the-art results. So in that work, they claim the best results so far for both sets, for this full set, as well as the subset of 50 labels. After that influential work, the many subsequent works, they propose new architectures, and they compare their proposed architectures with this CAMO architecture. Or in other words, they treat this CAMO as a baseline. And after the comparison, then, of course, their results are better. Therefore, they can claim that they achieve state-of-the-art results. And I'm talking about this MIMIC350, this subset. Now in this figure, you can see that the first row, that's the original CAMO paper. So we have the accuracy up to this point. Then of course, you can see that lots of subsequent works, they achieve better test accuracy. Therefore, they can claim that their architectures are better. Then the question is, did they really make progress on predicting this data set? Well, we discovered this when trying to reproduce some of their results. Then we find something interesting. So how hyperparameters were selected in the original work in this Camel paper? It turns out that this is what they did. For the full data set, in this influential work, they carefully tune hyperparameters by a validation process. And then they achieve very good results. Then for the subset, this is something they did. And you say, okay, I have a full set here. I have worked so hard to tune parameters, and I already got best parameters. Now I just directly use them for this subset. This is what they did. So say it again. For the bigger, more difficult one, they do hyperparameter selection. But then after they have obtained parameters, then when trying this subset, they just directly use those hyperparameters. So usually we don't think this is a big deal, right? Well, because you may not think this affects things a lot, but here's the situation. If you go to do a separate hyperparameter selection on this subset, now remember we are working on this subset. Then we do parameter selection instead of directly using parameters from the full set. Then we can see some dramatic improvements on the test accuracy. So turns out that their results can actually be much better if they have done a separate hyperparameter selection, so that most subsequent developments, actually, they cannot claim better than the original results. So that's actually an issue right now for the machine learning community. When you try to compare, say, an existing architecture and a new one, but if you haven't tuned things, then it's very difficult to make sure that one is really better than the other. This is actually a very interesting example. So some discussion. So this example is very intriguing because computational resources are not a concern. So usually for research on, say, hyperparameter tuning, then we try to propose methods in reducing the computational time, because usually that's a time-consuming process. You need to try so many parameters. But for this case, resources are not a concern. They can do a hyperparameter search on a bigger set, on the full data. Therefore, they can, of course, handle the smaller subset. The only problem is just they forgot to do that, or just a very minor misstep. So what we can see here is just, this is a very minor misstep, but it can have a profound effect. So we need to be very careful on that. But as a package designer, what I'm thinking is, can we have any way to avoid this? Of course, one solution is, well, you always do hyperparameter selection to enforce users to do that. Well, but sometimes users say, okay, I don't have enough time. I just want to try this configuration. Yeah. So this is an issue. But this is a good example. This is an interesting example. Yeah. We should try to think about how to address this for our users. Now let's move to the next story. Now the title of this story is about the casual use of advanced models. So let's see something I find out. Now let's ask a question. How most people do text or say document classification right now? So I talked to many engineers. And what they often do is like this. Because now they say, okay, BERT is a state-of-the-art model. Therefore, I go to take BERT as a pre-trained model, and I apply it on my data. And I run a fixed number of iterations. Then I get a model, and I can deploy it. And I find out that this is what many engineers are doing right now for their problems. So what is BERT? It is a large pre-trained model. Well, it has revolutionized many natural language processing topics. It is very useful for many NLP tasks. So such an advanced technique is actually great. But I'm going to show you that if you have a casual use of such advanced models, sometimes the results may not be that good. You may get poor results. And I'm going to give you an illustration. And for this illustration, I'm going to consider a paper written by Chokdis et al. This is a very recent paper published this year. So as I said, I'm going to use this paper for my illustration. So what does this paper do? The goal of this paper is actually to compare various BERT models on some legal documents. So this is about document classification. So after BERT, people proposed some variants, okay, some or say more advanced versions. So their goal is to compare those different models. And some properties of their data sets. Their data sets are either multi-class or multi-label. However, the number of labels is not large, less than 100. So that's the property about those data sets. And they report, in their paper, they report two tables on performance and time. So here, I copy their results. This is their table about performance, but not very sure if you can see all those numbers, but I will try to show some details. First, we have, they try 6 data sets. You can see 6 columns. So each column is about 1 data set. And each row is about 1 machine learning method. So you can see BERT here. And then they have Roberta, DiBerta, and the long former, etc. All those are variants of BERT models. And how about their evaluation criteria? They have this MuF1 and MF1. So MuF1 actually means micro F1. And this MF1 means macro F1. So essentially they use micro F1 as well as macro F1 as their evaluation criteria. Okay, so I have mentioned that they have quite a few rows of BERT models, but you may see that the first one is not a BERT model. They have this called TF-IDF plus SVN. So they have this TF-IDF plus SVN, but this actually means linear SVN, not kernel SVN. I assume you know something about TF-IDF, That means you go to use bag of words model, you generate lots of numerical features, and then you use the linear classifier to do the training. In terms of that, well, from this table, this linear SVM performs very well, especially for the last 4 problems. Now let's check the third problem. Now you already see those numbers in red color. So essentially for this data set, SVM is the best, better than all BERT models. Then for this called EUR-LEX data set, SVM has 71.3. But let's see who is the best. 72.1. Well, 71.3 versus 72.1. Well, not very different. Let's check the next one. This is a multi-class data set, I think. So SVM gets 87.2. The best one is 88.3. Yeah, 1% difference. Yeah, not very big. Then the last one, SVM gets micro 95.4. And the best is 96. Yeah, not very different, right? Therefore, we can see that for those 4 data sets, actually linear SVM performs quite well. But for the first 2, well, there is a gap. There's a gap. Now you can see that we have 64 here, but the best is 71. However, among the different BERT models, they are all about similar, all about 70. Right. So for this data set, all BERT variants, they are similar. And then there's a gap between SVM and the BERT. For the second one, SVM gets 74.6. Then the best is 80. We also see that BERT variants are similar, and there's a gap. But anyway, we can see that the last 4 data sets, this SVM performs pretty well. Okay, so now this is the table from their paper. That looks good. Okay, it shows lots of important information.
Excuse me,
Yeah.
Professor. What's the difference between these 2 measurements? What
Okay,
are they
okay.
trying
Yes,
to?
okay, that's a good question. Okay. So first, you know F1. F1 means like the harmonic mean of precision and recall. And the micro F1 means you consider all the labels together to calculate the overall F1. But macro is like a label-wise F1. So for the first label, you calculate the F1 value. Second, next label, you also have, for their prediction, you can have an F1 value. And you have F1 values across all labels and do an average. So that's a macro F1. So in general, micro F1 will be dominated by some frequent labels. Okay, but to avoid such a dominance, then you also want to consider macro F1. Therefore, it is reasonable that they consider both measures here. So I think they did a pretty good job. Yeah. So now, as I have said, we have shown their results. That looks normal. And here's their timetable. So the setting is similar. Each column is about 1 data set, except one exception. For a unknown reason, they missed 1 problem. Well, I don't know why. But anyway, that's not very important. The important thing is about those rows. Now you can see, oh, we have BERT. Okay, we have all BERT variant methods. Then we see okay, 3 hours, okay, several hours, something like that. Then for training BERT, then this is of course GPU time. But certainly you have a question. Where is the training time of that SVM? They didn't show that. So why training time of linear SVM was not shown? got interested in that. And we said, okay, let's try to do some investigation. But for that investigation, well, we try to use our software. Because in our this LibMultiLabel software, we have both linear SVM as well as like neural network solvers like BERT. First, let's try to do a direct run of linear classifiers. So in LibMultiLabel, we actually have 3 linear methods. Well, the first one is just the basic linear SVM and the logistic regression. But I'm not going to talk about details like, because SVM was designed for binary classification, but now we have multi-class and multi-label. But just some very simple settings. Then those SVM and the logistic regression can be used to solve multi-class or multi-label problems. Then I have 2 extensions. One called stretch holding. Here I only say that it is an extension of linear SVM or logistic regression to optimize macro F1. But I'm not saying to fit the test macro F1. I mean, there's an internal validation procedure of something like that. And in the end, hopefully we can get good test micro F1 value. Then there's another technique called cost-sensitive learning. That's another thing we have implemented. It is an extension of also of linear SVM or logistic regression. It can be used to optimize micro F1 or macro F1. Yeah, I don't have time to talk about details, but what I can say is that all those techniques, they were developed some time ago. They are quite mature techniques. And they basically need no parameter tuning. Therefore, what I did is just to directly run them, just to put data into the software and run those solvers. And I also try to do a direct run of BERT. Well, this is important because as I mentioned in the beginning, many engineers, what they are doing is they just do a direct run of BERT and to run it for several iterations, right? And for our package, we also support BERT. But we realize the importance of hyperparameter selection, right? As mentioned in the previous story. So I need to do that. Otherwise, if I don't do that, then you will question me immediately. So, of course, we check results with and without hyperparameter selection. So without means that just by using some default hyperparameters. And here I list the search space of hyperparameters. I consider something called maxima sequence length. Yeah, this is a parameter of BERT. Then learning rate, that's for stochastic gradient. And there's also a dropout rate. Yeah, a special thing is about maxima length. This is something special about BERT. And here's the result. Here's the result. The setting of the table is similar, is the same as before. So each column is about one data set. But I separate the rows to 3 categories. First is linear. So those 3 rows, they correspond to the results by running our package. Remember, I mentioned we have 3 linear methods there. Then we have 2 rows. That's the direct run of BERT by also using our software. But there are 2. One is called the default one. That's by the default hyperparameters. Then another row called the tuned setting. That means with hyperparameter selection. And this row is the BERT result from the original paper. Now let's try to check results in detail. Then, so we already know that the direct run of SVM results are already close to BERT, especially for the last 4 data sets. Right? I have mentioned that. But the 2 extensions, remember I mentioned 2 extensions of linear methods, thresholding and cost-sensitive learning. They make this linear method even more competitive. So earlier, in their table, only for 1 data set, this SVM is the best. But now, from the red colored values, you can see that already for 2 data sets, this linear method is the best. Okay, so this linear method is the best for those 2 data sets. And for this one, we have 86 something versus 87, yeah, slightly low, 95 and 95. So they are almost the same. But how about the first 2 data sets? Because earlier we mentioned that there is a gap. There's a gap. The direct run of SVM, we get 64 here. And the BERT, we get 71. And for the second problem, SVM gives 72. But BERT, you get 79. So there's a gap. However, for the 2 extensions, those well-developed linear methods, they make significant improvements. So now from 64 to 68.6. So that's closer to 71. And actually it gets the best macro F1. Okay, better than BERT. And for the second problem, from 72, now we reach 76. And the 63, now we have 68. Therefore, we can conclude that the 2 extensions, they are even more competitive. So it looks like for those data sets, linear methods are very useful. But let's check the BERT results by our solver. For the last 4 data sets, my BERT results are similar to the one reported in their paper. However, you can see that for the first 2 data sets, even after hyperparameter selection, I get only 61. Okay, so this is 61. This is not only much lower than 71 by their BERT, but even worse than the vanilla run of SVM, 64 here. This is very bad. Okay, I get 61 after hyperparameter selection. But this is a lot worse than their BERT and also worse than the direct run of linear SVM. And the same for the second data set. I get 69 here. This is 10% lower than their BERT, but even 3% lower than a simple run of linear SVM. So we can see that results of running our package's BERT are quite poor, even after hyperparameter selection. So what happened? Of course, then we need to do some study. Turns out that for the first 2 data sets, they use some more sophisticated settings to run BERT. It's not a direct run of BERT. What they did is they split each long instance to 64 segments. And each segment contains at most 128 tokens. Then each segment was put into BERT for training. After BERT, there's a so-called leading token called CLS token. So for those 64 segments, their CLS tokens are collected together, then put into another transformer to get the final output. So they did something not just purely BERT. That's the reason why they can get such a good performance. Now, how about running time? They didn't show, remember, they didn't show the running time, right? But because our package supports both linear as well as BERT, so we can do some comparison. And this table shows the timing result. Now you can see that for a direct run of SVM, for the first data set, this is 28 seconds. 28 seconds. And for the two extensions, well, they are more expensive, but still, this is 59 seconds, 1 minute, 38 seconds. But for running BERT, if we use default hyperparameters, then it's about 1 hour. With hyperparameter selection, then it's 5 hours. That's a huge difference, right? So we can see that methods based on linear classifiers are actually much, much faster. And moreover, for linear classifiers, we are running things on CPU, just one CPU. But here, for doing hyperparameter selection for BERT, I need to have a setting of 4 GPUs so that I can finish, say, things in 5 hours. So what are lessons learned from this investigation? First, from the best results for the first 2 problems. So we know that advanced models like BERT, they are really useful if you can use them in an appropriate way. However, sometimes if you just directly use that model, then you may get poor results. So you need a little bit like you need to be an expert. You need to know BERT and to know some trick. Say, okay, maybe for this kind of documents, I should do such settings. And then remember that here we say they split each instance to 64 segments. And each segment has so many tokens. How do you decide such numbers? Those are like magic numbers, right? Okay, so that's already an issue. That's what I said. If you do a casual use of an advanced model, then sometimes you may not get good results. But how can we avoid that? Actually, we already see a possible solution. We should have a strong baseline to help us to check the situation. We can see that for document classification, unless documents are very short, if they are long enough, then in such a situation, your sequence of words already provides enough information. Therefore, if you do TF-IDF features, then linear classifiers, then you can get a reasonably good model. Therefore, linear methods, they can serve as a simple but maybe strong baseline. And especially the training time is so short. Then you should do that. Because results from linear, they can help you to see if an advanced method has been properly used. So for our case, if we do direct run of BERT as well as linear, then immediately we see the problem. Then we realize that probably for the BERT, we should try some more sophisticated settings to make improvements. Therefore, baseline is important if there is one. Well, as I said, I want to skip this. So now I have some conclusion. Then we can have time for some to take some questions. So So in machine learning, we often search for better algorithms or efficient systems. Well, that's true. Yeah, we want those things. But if you are a package designer, to help people obtain satisfactory results, then actually we need more than that. You need to consider many other aspects. Of course, we hope to have some automated setting, but this is actually very difficult. So in a sense, this is already a huge research issue. Is how can we effectively guide users to solve their complicated problems? I always think that this is actually the final goal that we machine learning researchers should try to achieve. Okay, so thank you very much for your attention.
Now we have time for questions and discussions.
Yeah.
Thank you for this talk. Can I just very stupid question, like how do you tune, in your case, those hyperparameters? So do you just do grid search, or do you do something smarter in this?
You mean for the bird?
Yes, yes, yes.
For the bird, right now, it's a grid search. The reason is that I don't have many parameters. Now in this place, you can see that I haven't considered many parameters. For maximal sequence length, I have 2. Learning rate, I have 3. Dropout, I have 2. So I have 12 combinations. So yes, I do a grid search. Actually, there are some other things we can consider. In particular for BERT, sometimes we find out that the maximum number of iterations is quite important. But something probably we should also try to tune a little bit. Yeah. But the short answer is just grid search right now. Yes.
Also, basically, when I was trying to play with these language models, sometimes I also need to use different optimizers and Vedic, Adam, and this one. So I know so many things is changing the performance.
Yes, those are considerations. However, at this table, there's a 10% gap, right?
Yeah.
I don't believe that if we go to optimize to tune those things, we are going to achieve 7. To make 10% improvement.
But also very nice to see that your classical linear models are super good.
Yeah. We can say that linear classifiers are sometimes, I can say this is an often forgotten baseline. It's so simple and efficient. Then you should just do it and see what kind of performance you can get. That can give you lots of information. And for those document data sets, as I said, if they are long enough, then TF-IDF features, they already provide rich information so that you can get a reasonable model. But it's just that nowadays, many people, they don't realize that. Yeah.
Actually, I'm curious. In this case, did you try to reach out to the authors of this paper? See the hyperparameter values? The last one,
okay.
The performance was so good, right? Did you reproduce their result?
Oh yeah, I can reproduce their result. Okay. So here for this 71% result, they are very good researchers. They show all the details. They release their code. Therefore, that's the reason why I am able to find out. Say they do 64 segments of the document, and each has so many tokens. Okay, they provide. They are very good. They are very good, and we do communicate with them on some other details. Yeah, for some minor things, we even pointed out some minor errors in their paper. Yeah, so we do communicate with them.
I have a question. We all know that recently there are lots of pre-trained language models. They want more and more data and more parameters. But in practice, we also meet some situations. The data of the user is kind of different with the training data. The distribution is different.
Yeah.
And for deploy this model for the users, which one we can choose for the generalizability, or we choose SVM and or we choose pre-trained language models.
But you are asking the same question that I am asking here, because now it's just not easy to tell users what's the right way you can do. So you mentioned a point that pre-trained model, they get lots of, say, information from outside world, not your target application. So conceptually, this is very useful for things such as question and answer. You have such a short question, so you don't get much information. Therefore, in such a situation, we can roughly understand that a pre-trained model is supposed to be useful. But now we are in a different situation. Our documents are long enough. Okay, say you have news document, so each one is long enough. Then probably you just focus on the data you already have. Right. So another thing I didn't talk about is, how about the comparison between different neural network architectures for text classification? So in my table, I compare linear and the BERT. But how about other commonly used neural network architectures, such as convolutional neural networks or RNN? Turns out that it actually similar things we can say here, because those documents are long enough. Then for CNN or RNN, without the pre-trained model, they are quite competitive to write. So that's such a situation. But the problem is we don't know. We don't say, okay, for this situation now, we don't need a pre-trained model, or for that situation, we do need. Yeah, just not very clear.
Yeah, I wonder what do you think is there are lots of researchers that they follow through these pre-trained language models. What do you think, should we continue or not? Because we can't cover all the data sets, especially in the distribution. We just can approximate the distribution, but can get the real distribution. So they wanted to get more and more data. And as these results, they are for the testing, they have similar results with the traditional method like SVM. So what should we continue with? Should we continue with?
Oh, you mean for research? Should we keep develop? Oh, well, not very clear, but really we should still keep thinking about better models. Because for people proposing BERT, that's still something very useful to the
because some researchers said the ability of BERT have not been fully exploited.
Well, so for we researchers, you always need to think about, should you try to improve something an existing way, okay, like keep improving BERT, or try to see if the idea of BERT can be applied to other things such as speech or music data or something like that. But on the other hand, you can just think about something completely different. All those are possible for researchers. Yeah, there's no limit. Yeah.
Thank you.
I have a question.
It's fine. Yeah, next. Yeah, you can.
Maybe no, I think sorry.
Do you have any insight on why overall the performance on the first two datasets were worse than the other datasets? Is it the size or the domain or?
Oh, okay. Okay. So essentially, you are saying, okay. So that's a good question. So basically, we are talking about those two rows. Now for okay. So because if we compare if we check the last three rows, then you can see that our BERT results for the first two problems are much worse than theirs. Okay. But then the question is, what if we try the same technique for the last
for data sets. First, I haven't tried that, but we can try. Okay. For if you want to try that, then it's easy to do that. My feeling is, okay, this is my guess. My guess is those documents may not be too long. Therefore, their trick may not improve the performance very much. Right? That's one possibility. Or another way I'm saying about this is probably in the beginning, the two rows here were what they obtained. I think this is for the first two problems. How come that my bird can be worse than me? So then they try some improvements, and they end up with such techniques. So that's another possibility. Yeah, we don't know. Yeah, but you can go to try those things. Yeah. That's like a small research. Yes. So sorry. Yes.
Your table just showed the empirical result by parameter selection. With the selected parameters, we can achieve better accuracy. But the thing is, why the selected parameters do better theoretically? By that, I mean, can we leverage some causal information from this text data? By causal, I mean, can we analyze the data itself and finding some hidden structure? In that way, we may find some theoretical guarantee information. And you also mentioned causal, but I don't know we are talking about the same thing. So can we use
that's
that?
very difficult. But maybe you should think from the whole issue of document classification.
Yes.
Actually, right now, what we are doing is just a big data way. Even from TF-IDF, we just try to extract some features. And even for deep learning models, we're not using any semantic. Therefore, it is totally possible that you can come up with something completely different, but more useful for document classification. Yeah, that can be difficult.
I have a question is that I saw the original paper. They have they use model like long transformer, or I remember that they are using for like dealing with the long text because for the bird itself you only have the limit. You have a limit of the like window size, but I think on the first two data set maybe they're using the trick because maybe their document are too long. Or,
yes, exactly.
So is that
exactly.
So the performance also drops a lot for long transformer or for those models?
Yeah.
I don't know. Have you tried that?
Yeah. So those documents are long, right? Therefore, they do this trick. So they split document to several segments, and each one trained by one bird. Then
yeah, but they have like a long former or like a transformer XL. I remember is that like in their original.
Those are other bird variants.
Yeah.
Okay. Yeah, they are designed for long documents. That's right. But that's another story. Because at least for my package, I don't support those additional bird variants. Right now, I only have the standard bird. And here because what I want to tell you is that for many engineers, what they do is use directly run bird, and what kind of things you will get. That's the point.
Okay. And in the beginning of your speech, I thought you mentioned there is a problem that there exists like virus of the evaluation criterions.
Yes.
And from your software package or something, how can we like decide this?
The short answer is no. You decide. Users decide. Now we don't have the ability, okay, to tell you which one to use. But in the area of multi-label classification, yes, there are some guidelines. If your number of labels is not huge, then usually you do accuracy based. Okay, so you just say this document exactly has this subset of labels. But when you have many labels, then it's not realistic to do that. And think about, you can then, in that situation, it's like you do a recommendation.
you recommend this document is associated with those labels. Therefore, ranking-based criteria, they are more useful. Yeah, roughly that's the situation.
Great. Because of time constraint, maybe you can take the last question. If
Good.
okay, yeah, actually we are running out of time. So wonderful. Let's thank our speaker.
Yeah, so thank you so much.